Hello everyone. In today's lecture, we are going to cover the backpropagation algorithm in neural networks, which is also known as the backward propagation of error. As you know that a neuron is a processing unit where weighted sum of inputs is computed and then it is passed to an activation function to obtain the output. And a combination of one or more neurons make a neural network, comprising input layer, output layer, and one or more hidden layers. So the output obtained from the neural network is a function of inputs and network parameters. And in case of supervised scenario where we know the desired output, we can compute the error, which is gap between predicted and the desired output. And the learning objective of the neural network is to minimize that error. So now here we are considering the mean squared error, which is 1 by 2 d minus y whole squared, where d is the desired output and y is the predicted output. Now let's see an example of a single neural network with linear activation, and we are trying to fit this network to this dotted line. And here you can see that we are changing the weight and how it is impacting the loss here. Similarly, with the change of bias also, it is impacting loss, right? Okay, now from this example, we have inferred that by choosing the appropriate set of network parameters, we can achieve the goal of loss minimization. Now the question is that how we can choose the appropriate parameters. One way is that we randomly choose the network parameters and then separately update each and every parameter and check its impact on the loss function. So it is a rigorous task, and it's not feasible when we have millions and billions of parameters, right? So backpropagation helps us to update the model parameters or network parameters in a single go. It is an iterative process which consists of forward pass and backward pass. In forward pass, input is provided to the network and then processing is performed on that input, and then we obtain the predicted output y. Here, as we know that in supervised scenario, we already have the desired output. So we can compute the error here where forward pass ends. And then in the backward pass, we backpropagate that error to the network until input layer while updating all the network parameters. And the new parameter here in our case weight can be computed as the old weight plus the change in weight. Error. Now in backpropagation algorithm, delta W is proportional to the change in error with respect to weight, also known as gradient, and this gradient points in the direction of the function's steepest ascent. So by taking a negative sign here with constant of proportionality eta, the backpropagation algorithm updates weights in the gradient descent direction, and eta here is the learning rate which determines how fast or slow the learning is, the step size here in this graph towards minima. Now for computing delta W, we are considering two cases here. One where the neuron is in the output layer, and second case is where the neuron is in the hidden layer just before the output layer. Okay, so let's start with case 1 where the neuron is in the output layer, and here the neuron that we are considering is J, which is connected to I neuron in the previous layer, and the weight of the connection is WJI. Yi is the output that we are getting from I neuron. Okay, let's say Ej is equivalent to Dj minus Yj, where Dj is the desired output and Yj is the predicted output, and we can compute the error or loss function or cost function as 1 by 2 summation Ej square, where J belongs to C and C is the total number of neurons in the output layer here. And from here we can compute the average error, which is given as 1 by n summation of E, and here n is the total number of data instances. And here we are depicting the weighted sum as Vj here, which is Wij, Yi here, and here M is the total number of neurons in the hidden layer, here, this layer. And we can write the output Yj as phi of Vj, where phi here represents an activation function. Okay. Now, as we know that delta Wji is proportional to partial derivative of E with respect to Wji, it means that for computing delta W, we need to compute this term, right? And this term can be written as this multiplication of all these partial derivatives as per the chain rule. Partial derivative of E with respect to Ej, partial derivative of Ej with respect to Yj, and Yj with respect to Vj, and derivative of Vj with respect to Wji, right? Now, if we go to the previous equations, here you can see that that E is dependent on Ej, Ej is dependent on Yj, and Yj is dependent on Vj, and then Vj is again dependent on Wji, right? So if we compute the derivatives, derivative of E with respect to Ej, it is Ej, and derivative of partial derivative of Ej with respect to Yj, it is -1, right? And derivative of Yj with respect to Vj, it will be actually the derivative of the activation function, and which we will write as phi dash Vj. Okay. And partial derivative of Vj with respect to Wji, it is Yi, right? So after substituting all these values in the previous equation, we get this, right? Which is minus of Ej phi dash Vj Yi, right? And now, as we know this, so we can easily compute delta Wji, right? We already know the learning rate. This will be given, or we choose the learning rate, and then we have substituted this with this value, right? Minus minus got cancelled, and from here we can compute the new W, which is old value plus delta W, right? And here we are depicting this term Ej phi dash Vj as delta J here. Delta J is nothing but the error term, or we can also call it local gradient, which is given as minus of partial derivative of E with respect to Vj, right? Which we can write as this as per the chain rule. And mm, from the previous equations, after computing, we can get this value for delta J. That's why we are replacing this term with delta J here, right? And we can write the delta Wji as this in terms of delta J. Okay, it means that now Yi is known, which is from the previous neuron or layer, and eta is also known, which is learning rate. Now if we know delta J, then we can easily compute the change of weight, and then consequently we can compute the new weight from this delta W, right? Now let's see the second case where J is in the hidden layer here, and it is connected to neuron K, which is the output layer neuron, and the weight of the connection is Wkj, and J is connected to the previous layer neuron I, weight is Wji, and Yi is the output from ith neuron, Yj is the output from j neuron, and Yk is the output from k neuron, right? And in this example also we are considering the weight updation of Wji, delta j as we have just seen is equivalent to minus of partial derivative of e with respect to vj, and it can be written as this as per the chain rule, and this we already know, it is phi dash vj. Okay, the the derivative of activation function. Right now we need to compute this term, partial derivative of e with respect to yj. Okay, now this we can't directly compute because this error term is at this stage, at this layer, output layer, right? And for the hidden layer neuron, we don't have the desired output, right? So we can't directly compute this term. And in the current case, error is given as 1 by 2 summation of ek, which is computed here at the output layer, and k belongs to c, where c is the number of neurons in the output layer, right? And now this term, partial derivative of e with respect to yj, can be written as summation k, partial derivative of e with respect to ek, and then derivative of ek with respect to yj. So from this equation we can compute this derivative, which is given as ek, and this summation is for because there are multiple neurons in the output layer, right, which are impacting. So wji and wkj is impacting all those neurons. So while updating also we will consider all those neurons, right? And now again this can be written as this derivative of ek with respect to vk and partial derivative of ek with respect to yj. Now with this we know that ek is equivalent to dk minus yk, where dk is the desired output and yk is the this output, predicted output, and yk can be written as phi of vk, right, where phi is any activation function, right? So from here we can compute partial derivative of ek with respect to vk, which is minus of phi dash vk, which is derivative of activation function. Now for neuron k, this is same vk, we can depict the weighted sum as vk here, wkj, yj, and here m is the number of neurons in the hidden layer, this layer, right? And so from this we can compute partial derivative of vk with respect to yj, which is given as wkj. Okay. Now after substituting all the values, we have obtained partial derivative of e with respect to yj as this. And this we know that delta k is equivalent to ek phi dash vk, right? So this can be written as this, right? And now by applying all of this to the delta j equation, we have computed delta j as this value, right? Now we know delta j, and from this we can easily compute delta wji because we know this formula, right? And from this we can compute the new value of w, right? And this is applicable to any neuron in the whole network because we just need to know the value of delta and we can easily compute the change of parameter, right? We have seen that in the forward pass we have computed vj, vk, and then we got yk. From here we computed the error, then we backpropagated this error, we computed this error term delta k, then computed delta wkj to update wkj, and after getting this value we can use it to update delta wji using this delta j, right, and so on. And the predicted illustration of an experiment which shows learning of neural network where weights of the neural network are updated using backpropagation algorithm for learning sinusoidal function. So here you can see with time or iterations, weights are getting updated, which leads to reduced error or loss, and the predicted output is matching to the desired output after a few iterations. With this, I would like to stop here. Thanks.